This is a Nest thermostat. I'm probably sure many of you guys are familiar with this. A couple weeks ago I had an issue. I came home from vacation and I heard a weird rattling noise coming from my heat pump. I have a daughter and a wife, and they didn't want me to sit around and diagnose issues, so I called Isaac. They came out. He spent about 4 hours, $700 worth of time, and he found out what the issue was, and it was my Nest thermostat. Unbeknownst to me, and maybe even him, this Nest thermostat actually has has logic that's integrated into this base right here, and that was part of the problem. We never took this off. It looks thin enough, and a lot of the other thermostats I've seen don't have some type of logic in it. Everything's built into the thermostat, and you just plop it on, and you have the wires already connected to this. So the issue I ran into was that this right here has a couple of problems, but I actually fixed it. So I'll put these right over here. So if you open this up, you can see that there's a circuit board. And that's, wow, there's capacitors in it, there's integrated circuits, a lot of other stuff, and then there's Mosfets on the other side. So what we found out is that the reversing valve on the heat pump was on, receiving 24 volts when it shouldn't be. And the problem is the OB, which it controls which way the reversing valve is. When it's heating, it's normally off, or is not receiving 24 volts, but when it's supplying 24 volts, it turns the reversing valve on. So the solenoid was actuating off and on the heat pump outside, and it's only supposed to receive 24 volts when it's cooling. So something going on there. So what it is, I actually replaced these, and I actually did the video on this. These are called Mosfets, and they are a transistor. If you want to see, this is kind of the scale of it. Here's one of the bad ones. I replaced two that were in the circuit, and this is another Mosfet. Just luckily for me, I've played with Mosfets before, and I happen to have a very similar Mosfet, and it actually worked to replace these Mosfets with some of the spare ones I had just laying around. Not everybody has Mosfets like this and laying around, but it worked for me. Fortunately, mine are 30 volts, and these are and the circuit that's working with it's going to be 24, so it might not be the best idea. But one of the things with these smart thermostats is they use Mosfets instead of like a more traditional relay. And the relays they both have the purpose, the Mosfet and the relay. The switches are used on computers, we use them in their VRMs, and I use them in my circuit so I can provide higher current to my RGB strips here for this. So, if I just use these ICs right here, I can only provide one 5-volt RGB LED analog or 3 12-volt, but using the Mosfets I can greatly increase that, and then I needed all this other circuitry in it to help me with that. So anyway, so relays, I like them for this type of implementation, because what happens is, if they fail open. This fell closed, which potentially could damage things. Luckily it didn't, and I think it's a better implementation in my opinion. It's not going to get nearly as hot. These things, are been used fairly commonly within thermostats. But so they started using these Mosfets, which are great, but they have very fast switching speeds. I mean, it's far beyond this. They can turn off and on. Their lifetime as far as how many times it can be switched off and on. These are switches, if I didn't say that. This can switch off and on a lot more times in its life than this can. But the thing is, when you're working with thermostat, you don't need that fast switching speeds, and you don't need to turn it off and on, 1,000 times a minute or whatever. So I mean, like, you turn on your thermostat, it supplies power. You turn it off, it opens circuit, closes circuit. So I mean, you don't need to have you don't need to have a MOSFET. I mean, this is kind of overkill, and in my opinion, probably not the best implementation, because, again, a relay is electromagnetic switch that you send power through coil, and when the coil creates this magnetic field, it attracts a switch and closes it, so the circuit goes. Well, this is just a semiconductor, and you supply a voltage to the gate, and then it opens the drain to source, and it allows current to flow. But these can get a little warm, and they're very small. So again, I don't think it's the best implementation. But then again, I'm not a super EE guy. It's just, people I've talked to, a lot of the guys that work on thermostats or a lot of guys that work on HVAC units don't seem to really care for the new smart thermostats. And I'm wondering if it's partially because of that. So this thing here cost me $700, but apparently, I fixed it. So placing these MOSFETs, and you'll see in a video, I'll show you how I did it, and hopefully you'll learn from my mistakes. So if you have this on your wall and you have everything off, and you're wondering why it's providing voltage to your HVAC system, well, chances are you could have a MOSFET can fail closed, while a relay a lot of times will fail open, so you don't have that turning on. So what I plan on doing is I see two MOSFETs right here. My plan is to remove these two right here, and so I can take them off. Taping this off, so it's heat resistant tape, so hopefully I won't remove the rest of the MOSFETs that are on here. I decided to speed it up here, just to show you that I'm taping it off. As I said, this is heat resistant tape, and I'm doing a little bit of a voiceover because I can't multitask. So now I'm applying some flux. This helps quite a bit with soldering. So ready to go. So right now I'm using what's called a reflow rework station to heat up the solder that's under these two MOSFETs. I'm speeding it up. And the idea is you heat it up enough and it melts the solder, then you just remove the MOSFETs one at a time. You can see the pads are left after I removed it, so I'm not putting too much force. I'm just seeing when it's able to move. So that's what the bottom looks like. And here I'm going to add more flux. It's probably not the best flux to use because the board's really warm after using that reflow station. So right now I'm actually using what's called solder wick. I'm going to use this to clean up the pads a little bit, remove some of the old solder. I'm definitely not a professional. I'm definitely more of a hobbyist. So if you have any feedback and you do this more than I do, feel free. So the solder wick contains flux and copper, and allows the excess solder to stick to it. I'm applying more flux, and probably flux pin might not be the best because I'm seeing it disappear really quickly. Now I'm going to apply fresh solder to the pads, and again, I usually don't use this method. I don't generally repair boards. I've built fresh boards that don't have any solder, so, and as you're going to see, I put a little bit too much solder on there. Flux helps clean and allows the solder to stick easily to the surfaces that I want it to. Now I'm just making sure that there's solder on all the pads and try to get them evenly distributed. So again, this is not something I usually do. Most of the stuff I work with is fresh, no solder, and I have to use some more wick to remove the excess solder from the larger pads in the middle. I'm going to add more flux, but unfortunately the board's pretty warm that it kind of just evaporates too quickly. So now I'm going to apply the first MOSFET, the new MOSFET. And this is not technically the most ideal situation. Like, I would typically like a higher rated MOSFET, like a 60 amp or 60 volt. This is only 30 volt, and we're dealing with 24 volts for this, so for the circuit. So I'm just trying to align it. Use a surface tension, and also the flux helps bind it. So that one looks good enough. Now I'm going to apply some more flux. I'm going to apply the last MOSFET. And this one goes a little bit easier. And you have to watch out because the reflow station, it uses hot air and it can actually move other components. But this went better than I thought. So right now I'm testing the circuit. I have it plugged into power, and so I'm testing voltages and verifying I'm not seeing 24 volts on anything. So seeing, I guess 14 to 15 volts is okay. So I guess that's a low state. So now I'm attaching the Nest Thermostat. Fast forward to the boot up. So now the first thing I want to do is kind of test the heat mode for it. So as I enable it, it's turning on both the auxiliary and also the heat pump. I'm going to test the voltages. So I'm testing the green, which is a fan. It's receiving 24 volts. The fact that I see orange not produce 24 volts means it's fixed, at least from this test. Yellow wire, that's the heat pump. And the white wire is the auxiliary heat strips. This is for a heat pump with auxiliary heat. And right now I'm testing the cooling mode. And it takes usually a couple minutes because of the lockout. It's kind of a safety feature integrated. So I'm just going to kind of fast forward through it, do a few more tests. So I'm seeing nothing is currently on. So now the cooling mode is enabled and I'm testing, and now I get 24 or 25 volts on orange, which is good. And green, that means the fan motor's moving, that's what we want to see. Yellow, there's power going to the compressor. And we're not getting heat from the auxiliary strips, which is good. Thank you. Feel free to subscribe. If you have any questions, feel free to comment. Let me know if you have any questions. This was just kind of off the cuff, and I wanted to throw something together for other people. Good luck.